Okay, in this lecture we want to talk about the algebra of matrices. So these are like all of the properties really just in one big batch that you should absolutely memorize. And let's just recall three operations that we have performed, that we've carried out on matrices. So the first is addition of matrices. And two, if you want to add two matrices together, they both have to be of the same size. So both of these things need to come from that same set of all m by n matrices. You cannot add two matrices of different size. They both have to be m by n, right? Both have to have the same number of rows and the same number of columns. And how is that addition defined? How do we define this addition? Well, we define it in terms of the addition that you're already used to for real numbers. So the way you add two matrices is to add all of the coordinate-wise, all of the corresponding entries. Those are real numbers, and we absolutely know how to add those. So the sum of two matrices is just the matrix determined by the sum of all of the corresponding entries. And it's important to remember that if you add two m by n matrices together, you should wind up with an m by n matrix. And then we also define this scalar multiplication for an m by n, so any old rectangular matrix. You can take a real number and multiply the matrix by the real number. How should that go? Well, it should go how you think. The way you multiply a real number times a matrix is take all of the individual entries of that matrix and multiply by the real number r. So it's important to note, if you start out with an m by n matrix and multiply it by a real number, the result that you get is also an m by n matrix. And then finally, we define how to multiply two matrices together, but the number of columns of the first matrix has to match the number of rows in the second matrix, and order does matter. So the number of columns of the first thing, right, so P, has to match the number of rows of the second thing, so also P, right? And then when you multiply these things together, the result that you get, right, when you take an m by p and multiply with a p by n, the result you get is an m by n matrix. And how is that defined? Well, if I take this matrix capital A and multiply it by this matrix capital B, I get this new m by n matrix, call it capital C, and what are the entries of this matrix? Well, it's this sum, right? And this sum is the thing where you take the column of the first one, take the row of the first one, twist it, multiply it with the column of the second one, right? Multiply all the individual entries, and then add everything up. So we went over how to multiply matrices in the last lecture. So these are the three operations, and then we'll add one more operation in called the transpose. So we'll denote that thing with a capital T, and that's just the thing that takes a matrix and turns it into a new matrix where you take all the rows of the old one and make them into columns. So we'll get into that operation a little later. But we want to see how all of these operations interact with each other. So remember, you've got all these laws for real numbers like the associative property, the commutative property, and then you've got like an additive identity like a zero, and then you've got an additive inverse. So we'll write them all down. But most of these properties will look like ones that you've already seen for real numbers. But there are a couple properties that you might be used to for real numbers that don't carry over to matrices, and you need to be really careful about that. In fact, you should memorize all of the properties that do work for matrices, and then you should memorize all of the properties that don't work. There's not that many that don't work, but you definitely need to be aware of them and commit them to memory. Right, here are 10 properties that you need to memorize, and these are the properties for addition and scalar multiplication and how those two operations might be compatible, okay? So forget about matrix product for a minute. We'll deal with that. That's got its own theorem. We'll deal with that later. But these 10 properties, we'll see a list of 10 properties like this later for different objects, for like vectors and Rn. This same exact list is going to hold up. So I want you to memorize these 10 properties together. These are the properties, again, that link matrix addition with scalar multiplication. So over on this side, I'm going to give you a piece of paper, and these 5 properties will be titled A1, A2, A3, A4, and A5. A stands for addition, and these properties I'll label as S1, S2, S3, S4, S5. These stand for scalar multiplication. So 5 rules for addition, 5 rules for scalar multiplication. So what are these rules? First, addition of matrices is what we call well-defined. So in the math world, here's what that means. It means that this set of all m by n matrices is closed with respect to addition. In other words, if I take 2 things out of the set of all m by n matrices, add them together, the result is also going to be an m by n matrix. So closed with respect to addition. And then this other property that says if A is equal to B, that I can take this other matrix C and add it to both sides and I will still get equality. So just some stuff to keep in mind. You can always add the same thing to both sides, okay? You've done that plenty of times. Done it for real numbers, it's still true for matrices. Okay, moving on. Item 2, the associative property for matrices. If I add A and B together first and then add C to the result, that's the same thing as if I add B and C together first and then add A to the result. Notice the order does not shift. What does shift is where we write the parentheses, so how we associate, not how we order. So just keep in mind the associative property is about how we associate matrices via addition. The commutative property is about order. So the commutative property says A plus B is equal to B plus A, right? So A plus B is equal to B plus A. And the reason for that is because the addition of real numbers is commutative. Same thing up here. Addition of real numbers is associative. And then the identity matrix. So this set of m by n matrices has an additive identity. So for example, what's the additive identity in the set of all 2 by 2 matrices? Well, it's the thing that we call 0. So let's say 0, 2 by 2 is this 2 by 2 matrix with all zeros in it. So every one of these things has a 0 matrix, right? No matter what m and n are. Right, if this is 100 and this is 200, then m sub 100 cross 200 will have a 0 element. And it's the matrix, the 100 by 200 matrix with zeros in all of the entries, right? Easy enough. And so certainly, according to the way addition is defined, we should expect that the matrix with all zeros added to any m by n matrix will give us back the matrix A. So every one of these m by n sets has a 0 matrix, and that is the matrix consisting of all zeros. Given any matrix out, any m by n matrix, you can always find the additive identity of that matrix. So for example, here's a perfectly good matrix A. All right, so 1, 2, 3, 4. And then what should negative A be? Well, you want to be able to add this thing to this thing and get the 0 matrix. That's what an additive identity should do. When you add the additive identity to the thing, you should get 0. Well, this negative A should just be, make all the entries negative. Right, so you get this, right, if I hand you this matrix A with 1, 2, 3, 4, the matrix negative A, the additive inverse of A is this matrix with entries negative 1, negative 2, negative 3, negative 4. So these are all 5 of the properties for matrix addition that you absolutely should memorize. And now what about multiplication, scalar multiplication? Well, the rules look similar. At least a couple of them do, and the rest of them kind of look like some form of the distributive property or the associative property. So anyway, how does this go? Scalar multiplication is well defined. Remember, if I take a matrix, I scalar multiply, that just means multiply all of the entries by the real number r. So I still get, if I start out with an m by n matrix, I'm still going to get an m by n matrix after I multiply all of the entries by the real number r. And again, if a is equal to b and I scalar multiply both sides, the result will still be equal. So these two things are covered under well-definedness of scalar multiplication. Excuse me. Item 2 says that if I multiply a matrix by the real number scalar just 1, that's not going to move the matrix A. So I'm just going to get back the real number, I'm just going to get back the matrix A again. And then this thing says that scalar multiplication is compatible with the addition in the real number. So if I add two real numbers together and then scalar multiply by A, that's the same thing as if I scalar multiply A by R and then scalar multiply A by S and then add the results together. It should be worth noting, I think, in practice, computing this thing is a little easier than computing this thing, because this thing has 1, 2 operations, right? Add first and then multiply. This thing has an extra operation, 3 operations. This means multiply, right? Multiply and then multiply, so second operation, and then add. So that's the third operation. So add and then multiply is just 2 operations. Multiply, multiply, and then add is 3 operations. So it's probably easier to do this thing than it is this thing. So if you're handed a problem that looks like this, maybe change it to this and compute the easier thing. Same thing in item 4. This says that scalar multiplication is compatible with matrix addition. So if I scalar multiply the sum of two matrices, add the matrices first and then scalar multiply is the same thing as scalar multiply A by R, scalar multiply B by R, and then add the result together. So again, I'm going to say the thing on the left has 1 fewer operation than the thing on the right. And here's a thing that looks like the associative property, but make sure you sound out what it says. It says if I take A, scalar multiply by S, and then take that new matrix and scalar multiply by R, that's the same thing as if I just multiply the scalars together first and then multiply by A. So it seems like this thing might be a little bit easier to do than this thing. Right here you need to hit all of the entries of A by S, right? All of the entries, and then hit all of the entries of A by R. Or you could just multiply R and S together first and then hit all of the entries with the product. So it seems like this thing might have fewer computations to carry out than this thing. So that might be why these are useful. At any rate, you need to memorize these 10 properties. They're all in the book. They're spread out in a couple theorems. I would just memorize them all together. 5 properties for addition, 5 properties for scalar multiplication. All right, here's an example of how we might use this, these properties of matrices, of matrix addition and scalar multiplication to actually do some algebra that you're used to. So like solve for x, right? And this is what we call this section because those properties really, that's what allows you to solve for x really in a systematic way. So let's let A equal this 2 by 2 matrix, and let's let B be this 2 by 2 matrix. And we want to solve this equation for x, right? So this thing is a 2 by 2, this thing is a 2 by 2, and so we know that x must be a 2 by 2 matrix, right? Has to be. This would not make sense if x were any other size other than 2 by 2, right? Because 3x has the same size as x, and A is a 2 by 2, and in order for this to make sense, 3x has to have the same size as A. A is a 2 by 2, therefore 3x has to be a 2 by 2, therefore x has to be a 2 by 2. Okay, so just to straighten that out. So, here's how you're going to do this. Here's the equation 3x plus A is equal to B. how do you normally solve for x? Like in high school, what did you do? Well, first thing you would do is subtract a from both sides. So technically, that's the same thing as adding the additive inverse of a to both sides, right? You are allowed to do that. You're allowed to add a thing to both sides because addition is well-defined. Remember, that was part of the well-definedness. I'm allowed to add the same thing to both sides. And also, I know that this thing exists because of the additive inverse property. So it's like two rules put together. First, I know this thing exists, and second, I know I can add it to both sides, right? So now, what's next? Well, 3x plus a, so that's a quantity by itself, plus the additive inverse of a. That's the same thing as if I shift the parentheses over. That's just the associative property. So now I've got a next to the additive inverse of a. So what is that? Well, I know based on the additive inverse property, this thing is 0. So now I've got 3x plus 0 is equal to, and I'm going to go ahead and call b plus negative a. Just going to call that b minus a, like you're used to. Just same thing, different notation. But now, this is the same thing as saying, and I left this step out, 3x plus 0 is just 3x. So this is 3x is equal to b minus a. And the reason is that's the additive identity property. So that's the additive identity property. You know that when you add 0 to anything, it doesn't move. So 3x plus 0 is just 3x. So now you get 3x is equal to b minus a. And so remember, trying to solve for x, I need to get rid of the 3. So I'm going to multiply both sides by the real multiplicative inverse of 3. So I'm going to multiply both sides by 1/3. I'm allowed to do that because scalar multiplication is well defined. It's covered under that part. I'm allowed to scalar multiply both sides by the same thing. And I ran out of room to write, so I'm just going to have to say it. So now I can reassociate. Remember, scalar times a matrix and then multiply by a scalar is the same thing as multiplying the two scalars first and then multiplying the result by the matrix. So that's just that associative property that scalar multiplication looks associative. So now what's 1/3 times 3? Well, now this is a statement in real numbers. Excuse me, an operation in the real numbers. So 1/3 times 3 is just 1. And this is the same as before. Well, what's 1 times x? According to the property, we know that 1 doesn't move any matrix when I scalar multiply. It's just, what am I going to do? I'm going to multiply every entry of x by the real number 1. That's not going to do anything. And so now I see that x is equal to 1/3 b minus a. So here's our solution. X is equal to 1/3 b minus a. So all I need to do is compute this thing. So that's what we'll do now. And that's an easy thing to do. So 1/3 b minus a, it's 1/3 this matrix, or sorry, this matrix minus this matrix. So -3 minus 1, 4 minus -2, 2 minus 0, 1 minus 3. So now here I get -4, here I get 6, here I get 2, here I get -2. And now just go ahead and multiply through by 1/3. So here you're going to get -4/3, here you get 2, here you get 2/3, and here you get -2/3. So here's the solution to that original equation. I think it was 3x plus a is equal to b. So here's the solution. This thing is the solution for x for this equation. So that'll do it. All right, a few other properties for scalar multiplication having to do with the 0 matrix. So We'll let A be any m by n matrix, so some rectangular matrix with m rows and n columns, and we'll let R be any real number. And I want to differentiate between the zero element of the set of m by n matrices and the zero element of the real numbers. When you see 0 m cross n, that means it's the zero matrix that lives in here. So, what do these four things say? First of all, if I scalar multiply the zero matrix by any real number, I'm going to get the zero matrix. And here's sort of the reason why. You know, just using a 2 by 2 case, we can get a feel for why this is true for any size matrix. So if I take R and scalar multiply this 2 by 2 zero matrix, then that's the same thing as multiplying every entry by R. So now these are just real numbers. The real number R times the real number 0 is just 0. And you get that in every spot. So R times the zero matrix, the 0 in the 2 by 2 matrices, is right, R times the zero matrix in the 2 by 2 matrices is going to give me the zero matrix in the 2 by 2 matrices. So, and you get a similar thing in item 2 here. If I scalar multiply any matrix by the real number 0, that's the same thing as multiplying all of the entries of A by 0, and so that's going to return the zero matrix. And then if I scalar multiply the matrix A by the additive inverse of the real number R, that's the same thing as scalar multiplying A by R first, and then taking the additive inverse of the resulting matrix little r times big A. And that's the same thing as taking the additive inverse of the matrix A and then multiplying by the real number R. So these all look alike, and they're all equal, but they all say different things, even though they do the same thing. They say something different, so sound it out. And this thing here, if a scalar multiple of a matrix A is equal to 0, then either the real number R is 0 or the matrix A is the 0 m by n matrix. So again, these things are all easy to see why. If you just do a few examples, right, all of this will pop right out in the wash. So go ahead and memorize these additional 4 properties about the zero matrix and scalar multiplication.